maintainers of Remoteproc, rpmsg, and hardware spinlock. First, Remoteproc. It's a framework for controlling the lifecycle of coprocessors in a multi-processor, normally SoC. Loading firmware, booting, shutting them down. And what differs from, for example, when you have a normal device with some firmware, is that generally the hardware doesn't have a function itself. So the only thing that the device driver does is boot and shut it down. So we have a core, and then we have Remoteproc drivers. These implement the specifics of a certain DSP or whatever. We allocate the struct, and or we allocate some context, and we add that to the core. And when the driver is done, we delete it, which tears it down, and we release the references. The operation struct that we have two operations of importance. One is start, the other one is stop. So when someone or something is trying to boot or tells us to boot, it will do resource allocation, and then it will call start. And when we're done, or when someone tells us that we're done, they will call stop, and then the core will tear down those resources. And currently there's a separate struct for firmware parsing, which in this default environment supports an ELF format. So in the ELF file, we have a resource table describing the resources needed by the firmware when it's loaded. So we have memory carve-outs where normally the firmware is loaded, the code and the data, but it could be other things as well. We have IOMMU and trace buffers. That's for a specific use case or specific things. And then we have VirtIO devices, which is used for communicating with the running processor. And that's, so the VirtIO devices would then be, it could be network interfaces, serial interfaces, or rpmsg, message passing so the core, or the ELF loader and the core in collaboration loads this resource table, sets up all these resources, and then it calls start in your driver. One of the things we have here is that up until now it's been fine with just listing what kind of memory regions in size that we need. There is limited support for controlling your allocation limitations. For example, if you need allocation to end up in a certain area of RAM, or if you need a specific position. So the resource table have the information, but the implementation haven't looked at it so far. But the allocation of both the memory carve-outs and the VirtIO devices, or the V-rings associated with VirtIO devices, are done in the context of the Remoteproc driver. So we have some control of it, but there are definitely some cases where people need more granularity. So the ongoing work or the work that's happening right now. So traditionally, the model has been that either you have your own Remoteproc registered, and you have some sort of third-party driver with a reference to your Remoteproc, and it will tell it to boot and to shut down. is, in the event that there are VirtIO devices associated with the Remoteproc, those would trigger the Remoteproc to be running or not. So one of the problems with how this had been implemented is that as soon as we found a VirtIO device, we would register that with a VirtIO device in the resource table. We would register that with the VirtIO framework, which would go out and try to find the backing storage for the communication channels, which would trigger a boot of the Remoteproc. So in the event that you would list several VirtIO devices in your resource table, when we actually boot the resource table, or boot the Remoteproc, the resource table wouldn't be fully parsed, so we might not have set up all the memory regions, and we definitely haven't allocated all the memory for the subsequent VirtIO devices. And there are some requests for being able to have this third-party controlling thingy to control the lifecycle of the Remoteproc, even though it has VirtIO devices. One could think of, for example, if you have a controller and then your firmware exposes a serial debug channel over VirtIO, you don't want that to control it, you want this other party to control it. So I introduced a property on the Remoteproc for the Remoteproc drivers instead, that you can set depending on if you're expecting to be controlled by a client or if you just should boot when the firmware is available. That means that the behavior of the Remoteproc no longer is tied to the listed VirtIO devices in the resource table, but to some specific, or to this specified flag. And as a side effect, that simplifies resource handling quite a bit, because previously we had, once we found that the firmware was there, we would trigger the initialization of VirtIO devices, which would then take a second pass at the resource table and allocate all the resources, if there was a VirtIO device. So now it's much easier. It's when we decide to boot, we parse the resource table once, and we set everything up, then we start. Maybe I should say that the auto boot feature is currently in Linux Next, and I'm intending to have that in 4.9, but Sumanana was kind enough to find some issues with it, so I have a few bug fixes that needs to be in place before 4.9. Then we have the next ongoing thing, which is in the case that the resource table have a list of carve-outs, for example, and we want to be able to control where in physical RAM those ends up. We need a mechanism to amend the information in the resource table. Like in my cases, I have memory regions in device tree that I want to merge with the resource table. And that also allows us to control, especially the memory carve-outs.
How will it work today? It just takes some, this is just a size?
It's DMA allocoherent.
Okay, so it just takes
by
some
size.
of specified size?
Yes. And that's, so in the case when you have an IOMU, so your Remoteproc sits behind an IOMU, that's fine. But if you don't, then you need this. We need the merging part, especially for the resource table, when it's used both for the firmware to communicate what kind of resources you need, as well as for the kernel to communicate where those resources ended up in RAM to the firmware. So this would be a way for us to amend that and propagate that information to the other side. So the various proposals that we have been looking at and that I'm looking to have is an API where we can programmatically allocate resources, and we could then do that from the driver, and when the resource table is parsed, we can try to merge the information from the two. And we can do some sanity checks that, for example, the firmware don't ask for 1 meg and we only give it half a meg. So we would be able to reject or stop it from boot then. Having this API would allow us for the use case when we don't have a resource table in the firmware. So especially like in the Qualcomm case where most of my drivers coming from, we have a fixed memory region that is for the firmware, and I would like to use the core's handling of carve-outs and communication mechanisms, so I don't have to encode that in my driver or to write that in my driver. There are some other cases where we have non-resource table data structures describing the same information. Yeah, it would be good if we can reuse the core infrastructure without relying on the resource table format. In these cases, the solution we have today is that we can, in the firmware operations struct, we can overload the load function, and we can programmatically build up that blob of information and pass that to the core. But as that's on-disk structure, it's kind of messy, or it's really messy. Yeah, again, have an API to register these kind of resources. So there's, yeah, well, it could be the same API.
But we are the one just to register carve-out resources.
Yeah, so this is mainly for carve-outs.
Yeah.
One would, I mean, trace buffers would be easy, and IOMMU mappings would be easy. Vrings is complicated for the fact that in most cases we would need a mechanism to communicate their placement to the other side.
Yeah,
And
if we are IPC, we need
yeah, so yeah, we need some sort of mechanism to communicate that. So first and foremost, I would like this so that I can reuse the carve-out logic in the core in the cases when we don't have a resource table. So the next thing that came up in this discussion was that we wanted to be able to want the possibility to direct vert.io buffers into certain memory regions, for example, device RAM. So we want to be able to IRE map a device memory and use that for the V-rings of the vert.io device. Looking at how the core handles things today, there is a structure that holds the information related to a carve-out, which is fairly generic, or if we treat that as a generic just memory segment, and we rely on previously introduced merging mechanisms, then we would allow this API to register IRE map regions or carve-outs or any specific type, and when the resource table is merged, it would be the same data structure. So in this, the suggestion here is that we, instead of operating on the resource table, we parse the resource table into some generic data structure and operate on that, and that would allow us to have different types of memory in that same data structure. If we do it like that, then the merging mechanism, we could use that so that when the VRing memory is allocated, if we fall that back to this generic data structure because it's no longer in the resource table, we have the mechanism to use carve-outs, or we can use the core's carve-out mechanisms for backing VRings, and it's now possible for Remoteproc drivers to control where their VRings end up. So the only concern we have then is that if the Remoteproc driver uses this API during its probe, for example, we would allocate all the resources at that time, even though we haven't booted the system. So I made a prototype where I build this data structure, but I don't actually do the allocations until the boot time. Yeah, that turns out pretty well. So
So that means that your airport specific, platform specific driver will know the resource table to know exactly what should be allocated to the dedicated memories. Because for the pairing, it's not like about the others are defined with some specific attribute the resource table.
yeah,
So the size may be different
yeah.
from one viewer to the other one, the alignment and so on.
Yeah, so for carve-outs, it's rather easy to merge because we have a name.
Yeah.
For VRings, we have a device address and we have a physical address, so we could match on those. But the feasibility of using this in other than the most static cases is up for debate. Yeah, I hope to see some discussion on this once
Yeah,
I.
it seems that it's a hot topic.
So
Even if you have physical address at any address, that means that you can allocate anywhere. Your airport specific, platform specific driver would know that he has to use the internal one instead of standard minimal or current features. So that's where I'm not sure that we can handle it as covered. Just because the initial batch I sent, where I was proposing to rely on the platform-specific driver to do the allocations, it's just because even if we don't fix the physical address,
Yep.
we can use a specific allocator.
yes, so
There are so many cases.
yep. So the proposed patch was that the core would, when allocating VRings or carve-outs, first try to call into the Remoteproc driver and see if it wanted to allocate the memory, and then fall back to using the alloc coherent. I fear that the implementation of Remoteproc driver will be rather complex. Or rather, if we have a couple of carve-outs and a couple of VRings, the Remoteproc driver would probably end up more or less having a switch statement asking, or looking at some predefined list. Is it this memory region? Then I should allocate like this. Is it this memory region? Then I should allocate like this. So I think it's cleaner to pre-allocate or to register those resources beforehand and then have the core match them. Also because it would then match with the previous suggestions. So it ties in better with those. But it's a bad patch to start with.
Just of the pre-allocations, don't see how to be providing the resource table information to your airport specific driver to do the right pre-allocations.
Yeah, so as soon as the Remoteproc driver starts to inject or register resources, there becomes a contract between the resource table, the Remoteproc driver, and the firmware. And today we only have that between the resource table and the firmware. So the question is how much it would be used for things outside the carve-outs. Because the number of VRings or virtual virtual devices that you specify in a resource table that your firmware should expose, that feels like that's a firmware specific thing. But if we say that that's not a property of the Remoteproc thingy, but rather a property of the firmware, then also we don't have, then it doesn't make sense for the Remoteproc driver to try to handle some of those allocations. I think we will discuss this one more. This one I want because I have some memory regions in device tree that I want to use as carve-outs.
So beyond my take on that one was like, either way you would have to add backend units to your Remoteproc driver, especially the moment you say you want to control specific placement. No matter how you look at it, it's all over, and Remoteproc core cannot do much on that front. So either it will like do an ops and require Remoteproc driver to say, because like it's agnostic from the Remoteproc core's perspective, or the other way, so as you were suggesting, which is like inject resources, and as you're injecting resources, you're already injecting things.
Yep.
But either way, both of those logics will.
Yeah. So in the case when we want a specific physical placement, the question is what that means, and if it means, and if we don't want to have to pre-allocate these remap regions, for example, then I think that having this callback from the core into the driver, I don't think it will scale very well when we have multiple drivers.
It's optional, right? And the ops are optional. So
Yes, it's optional for each driver to have that, but it's not optional for me to maintain all the code that will be duplicated between the drivers.
Yeah, but I agree to memory map or memory map carve-out regions, but for Vring, how do we verify that requested address, for example, you have the requested physical address and size and element. How do we verify that you have no overlap? That means that if the resource table of your firmware has any error, you won't verify with just memory map. With allocator,
If we,
fail.
yep.
So that's why for Vring, I prefer to rely on allocator.
Yeah, but if we match the Vring allocation on a full carve-out allocation, so we don't like the trace allocations, they can just be that can be a partial snippet inside a carve-out. But if we match it to be a full carve-out, so we only allow exact matches, then we wouldn't have the overlap problem. Yeah. The question here is also how static is this use case? I mean, when I build my device, do I know exactly where that firmware, what kind of resources that firmware has? And if I don't know that, then how can I assist it in allocating these memory regions?
Completely depend on the SOC and the different use cases. As soon as, for example, on sandboxes, we apply security, all the mapping is fixed.
Yep.
So we know everything, and that's where we need to clearly predefine all the different areas. Now we have nesting only one remote driver, managing several coprocessors. It's the same coprocessors, but doing audio, video, security stuff, and so on. And we are tuning rpmsg link hyperlink to message to rpsm. We are using, for example, rpmsg to communicate with some paper model
But in all these cases, that would be at the time when you build that software for the SOC, so not the firmware, but the SoC. So when you define your device tree or your board file or whatever, at that point, I presume that each Remoteproc would get its available resources, like how much memory does this thing how much memory is this thing allowed to use? For this particular Remoteproc, I want you to use these particular device memory regions, or is that completely dynamic later?
Depends.
Okay.
There
Yep.
is some coprocessor for which it's fixed,
Yep.
predefined, and some other where the firmware itself is position independent, where we completely rely on the Linaro current, and we rely on the current remote implementation to do the modifications.
Yep. So I think in a lot of these discussions, it's obvious that there are two types of use cases. So one is the predefined firmware using predefined resources, in many cases in a predefined spot in RAM, for example. And there it's kind of easy to, well, either you encode the information in device tree or in your resource table, or there's some, or you get the firmware from some firmware team and you amend it with resource information from device tree. And then we have the more or less completely different set of systems where we have the TI PRUSS, where I as a, is it BeagleBone Black, where I can write my PRU firmware and I can tell the kernel, hey, I want to run this on the PRU for a while. So it's not at all tied to the system configuration, but those resources are entirely tied to the firmware, and we need a mechanism to take this piece of firmware and load and unload it. And that ties into, in the Qualcomm case, we have a similar setup where we can build binaries and we can load them into running DSP firmware. So the firmware has dynamic loading, basically. So I'm wondering if we shouldn't keep those separate and try to figure out the sane API for all these temporary execution instances, where we have some sort of binary. We want to load it for a while into either into a clean processor or into firmware on the processor, and we want to have a standardized or fairly standardized method of communicating with that firmware as it's running. So I think, I definitely think we need to discuss the dynamic case, but I think we need more stuff to get that in place.
We definitely need more API for the dynamic case that we're talking about, especially like if you're going to be talking about dynamic loading, then it's already provisioning, right? So that means like at least I think a couple of API that I see that are using right now is just loading pop-up map and unmap, kind of like again pages to map them into your device memory.
Yeah, so it's,
Where you have an identifier,
yeah.
right?
I mean, you could think of a setup where if I have my TI board, I would have certain resources available, certain memory regions available, and I have to write my firmware to fit into those. Or you can have something way more dynamic.
But in the cases of MMUs that are mainline MMUs, it's rather easy because your firmware image are already, your paper map is already virtual machine, right? You don't have any restrictions there. It's just it dictates where your backend is coming from.
Yep.
But in the cases where you're saying there is no MMU, then you're already tied to fixed memory because like you're saying all your positioning is written into the whole way, which would mean like
question is how much logic we want to do with, for example, completely disjunct memory regions. Do we want to, and for carve-outs it's fine because we have a name on them. But for V-rings we don't have any real identifiers. We can't say, the driver can't say, here is the memory region I want for VirtIO device number 3, V-ring number 4, because that API would be terrible.
If we stay with the true bearings, like today it's easier,
Yeah.
in one way, but as there was discussion to increase the number of bearings and the support of the profile.
Yep. So for the use cases supported in the kernel today and in the near future, the static model will work just fine. Beyond that, we have the TI PRUSS. SD, I guess, have something similar, and we have the Qualcomm hexagon loader, I would like to see one of those being moved forward towards mainline, and that we model it after that, rather than model it after some out-of-tree solution. So I think if we solve the static case, then we solve everything that is presented today, and then we build from that. And I think this will work when you know what the firmware is. So when the driver knows what the firmware will present in terms of resources. If it's completely up to the firmware, then you can't have you can't have those kind of restrictions. The other thing that's in the workings, and it's almost done, is so at the places where we register and unregister VirtIO devices, in the Qualcomm platforms we have almost an equivalent of rpmsg. rpmsg or the other VirtIO thingies. And there are some other cases where, for example, you have a video for Linux driver that exposes some functionality from the firmware, and we want that video for Linux driver to be available when the firmware is available only. So we have a need to be able to model thingies that follow the running state of the Remoteproc. So instead of having these VirtIO register unregister calls, I propose that we have a slightly more generalized method where you can register VirtIO devices or SMD or G-Link or maybe even platform drivers, that once the firmware comes up, we probe that, or we register that thing, and once the firmware goes down, we unregister it. One of the questions that I don't know really yet is should a core deal with some of these standard types? Should we have like a helper function in the core to say my device tree child is a platform driver, do the rest for me? I think there will be corner cases. The proposal I'm about to send out is just that the driver can register these devices, and they will be probed and removed as the firmware comes up and goes down. Yes? do you have your I2C? Do you do your I2C communication with the Remoteproc, or does it implement I2C communication with some devices? No. So yeah, the regulator case, that's in that case, well, we basically have that in the Qualcomm case where there are channels appearing that would match with our resource power manager, which when that probes, we register as at the regulators. One could think, for example, that once you boot the firmware, it presents well, VirtIO network devices or some odd non-standard communication method for controlling the function, and maybe there's a audio chip there. And I think that in all those cases, you want, if you model that as you have the Remoteproc and then you have your functional driver separate of that, then it's easy to tie them together and have that MFD driver, whatever, to tell the Remoteproc when to start and when to stop. But if you have complex firmware and that might, and that there is a chance that that might crash, we might need to restart it. And the restart will be, well, the way it's implemented is that it's an asynchronous operation. You tell the Remoteproc, hey, you crashed, or the Remote core that, hey, this driver crashed, and it shuts it down. Probably we want to be able to extract some core dump, some memory for debugging purposes, and then we want to start it again. And if we model them next to each other, then we would need to come up with a mechanism to notify the MFD when that thing is up again, so that it can make sure to reinitialize its state to match the firmware state. So if we instead model that device as a child of the Remoteproc, then we would have a direct mechanism to tear that driver down and put it up again once the firmware is available. And we wouldn't have to care about if collecting that core dump takes 5 minutes or 2 seconds, because the child driver would completely follow the firmware's life cycle, or the running state of the Remoteproc. Yeah, so I haven't seen a use case yet for where we actually need to be able to signal some independent device. But I definitely see the use case where we need to reset the state of a driver that handles a driver for a function exposed by the firmware.
I have some use cases with some coprocessor in charge of sensors, for example.
Yep.
And another message is SPI-like communication services. And services are internet, all the sensor functions. But we have user space services, for example, just for Programmatic.
Yep.
And user space can decide to stop the processor to update the firmware to restart. In that case, we have to stop all the kernel services related to the coprocessor. So it does as substitution.
So does that mean that you have a user space thingy that is in control of if the Remoteproc should be running or not? And depending on that, you have kernel services that should be
Which are registered to the register.
Yep.
But it's not in the Remoteproc. And we are thinking to move the Remoteproc, but such feature are missing.
But for those components that then are not children of the Remoteproc, or doesn't relate that like that Remoteproc, how do they do they need to know when the Remoteproc come and go?
That's a need. We need to know. Today we have dedicated ST driver for that. It means firmware running, able to start like when everything is servicing.
Hmm?
But if we want, for example, to upstream and to have a generic growth control,
Yep.
we need to move to our Remoteproc. And as we don't have rpmsg and no Etherpad, we don't have these mechanisms to protect generating services and to remove services when we are stopping the microprocessor. So definitely that's something.
But would there be a problem to model those as children of the Remoteproc node? Are they just platform drivers, or are they?
It's LAD feedback, so it's platform driver.
Yeah, no, because like I said, there are several.
After we should think how to connect to Remoteproc,
Hmm?
how to connect on trade.
Yeah. So the use cases I've seen today, I have. So it's either the Verti or the Qualcomm equivalent, or there are some platform drivers that could follow that life cycle. And then we have a couple of proposals for having this. Well, first and foremost, we're having a device tree p-handle reference to a Remoteproc to be able to control it. And Rob said, why you need this? And yeah, so far I haven't seen an example where it's needed except for the peer USS. And I don't know how you would model the peer USS as in a device tree environment, because it's not hardware. It's entirely a software construct for controlling hardware. So the question is then, is it valid to have this kind of control mechanism just living in the kernel for the sake of controlling the Remoteprocs? And another thing is, in the cases when people want to start and stop the Remoteproc from user space, I think there was a sysfs interface for this, or there is at least a proposed sysfs interface for it. But again, it's a matter of what are the actual use cases, and we need to discuss that, and we need to see some code for that approaching mainline before we decide how we want to model that. And we want to see what happens if I have an internal consumer, or well, if we come up with a use case for an internal consumer, and that starts a Remoteproc, and then user space come in and say stop. What does that mean? And when is that valid? And there's definitely the problem of when do we actually start Remoteprocs? And the way it works with the auto boot thing is that when the firmware is available, then we boot it, or when there is a third-party component asking for it to be booted. And those cover the current set of system designs. So I would really like to see the other, see what kind of other solutions there is that would like to have this or need this. Yeah, we definitely need a mechanism to when a Remoteproc misbehaves to extract a memory or a core dump from that dying Remoteproc. I'm going to take another look at the TI. There seems to be some TI code from 3 to 4 times that does this somewhere. I'm going to take a look at that. But the general approach is when we're going down, we want to back up memory that is going to lose power when we turn the CPU off. We turn the CPU off, and we would preferably then generate an ELF file with segments that the Remoteproc driver or the resource table have built up. And with all these APIs introduced previously, where drivers or the resource table would register generic resources, we should be able to turn that one around, so there isn't so much coupling between the core and the resource table parser, but rather we have a resource in the Remoteproc operation structure. We could have just a parse, which would default to the current behavior, but be driven by that parser to register resources with that, rather than the core pulling them out of the resource table. The benefit of that is that if you have alternative mechanism or alternative file formats, it becomes much less awkward to support those. This is, it's just upcoming refactoring that I hope you.
You haven't posted anything on this, right? You haven't posted anything on this.
No, I haven't posted it yet. Most of these things I have implemented it far enough so I can see that it's viable, and then then we have a long discussion on your two threads and some other things. And one outstanding issue, or the biggest outstanding issue is in a lot of these systems we have firmware files that are huge, and huge can mean over 100 megabytes, and we can't put those in an init RAMFS. There are in some cases even legal requirements that forces us to put it somewhere else. So we would put them in for example, in a typical Android system, we'll have a system partition that once that is mounted, we would have the firmware available. And we need a mechanism to signal the kernel when that firmware is available so it can boot the Remoteproc. And this becomes sort of equivalent to having a sysfs entry where you say start, but hopefully less specific. There are two working options for this today. One is to use kernel modules. If you load your Remoteproc driver once the firmware is available, it will be there. Another one is use the user mode, the user space firmware loading. There is a remnant in that code for, there is a remnant in the firmware class that if it fails to load a firmware file, it will fall back to wait for some period of time and it will send out the U event, and it will wait for some time for user space to feed the firmware into sysclass firmware. No one supports this since like 3 years back when systemd dropped it, but it works perfectly.
A couple of folks have added it back, I think. They work with, I believe, the general direction there is not.
Okay. Yeah, and Dimitri, the input guy, suggested that we just have another daemon listening for these U events and providing the firmware with the policies needed to deal with late mounted firmware or late mounted file systems. So another thing is, in a lot of these cases we have very similar firmware, but different devices have slight variations of it. So how do we deal with, well, essentially naming of the firmware files if we have a generic firmware blob? This is the kernel modules and fallback works, and I hate to force people to use kernel modules, and I heard that Google didn't like kernel modules in Android anymore, so it would be good if...
I think it works fine in Android, because I think Android even with built-in, it works fine without having to rely on, because I think they do something fine on the loading. They're not using the traditional UTF, that's necessary. So I think we never had a problem doing built-in.
No, it works. The question is if they want kernel modules. There was a patch posted that introduced a like a checkpoint thing where user space could tell the kernel when the file systems are available. I tried to discuss with Linus Torvaldsson in that thread that I want something like this, and he does not think that this is a valid concern. He wants us to use kernel modules. So if anyone talks to him, it would be good if we highlight that. So, so the other part, rpmsg, it's a framework and a wire format for exchanging packets of data. And what differs it from a typical network thing is that it's all over point-to-point channels, although logical, but still. And it's not Remoteproc, it's Virtio. So you write an rpmsg driver, and you tie it to, or you register it with the core, and when there's a channel, a related channel available, your driver will be probed, and when the channel goes away, the driver will be gone. You have basically two functions, or three functions. You have, you can send data on this channel that you're probed with, and you have a callback when there's data on that channel. And then there are some variations of the send, but and the core has the create endpoint and destroy endpoint APIs if you want to try to associate with additional channels. So if you have a driver that needs to communicate over multiple point-to-point channels, it can use this API to try to open it, although it might not be there. So so the secondary channels you have to sort of expect that they follow the primary channel's lifecycle. In the current mainline implementation, rpmsg is the Virtio ID rpmsg thing, so it defines the wire format and the API. When I moved the Qualcomm shared memory communication method into mainline 2 years ago, I think, I modeled it so that it would be very similar to rpmsg, mostly because I figured it would be easier to get it through review. The structure and the life cycle of the SMD devices and the rpmsg devices are very similar, but the way we deal with memory, so with the V-rings and the buffers, are completely different, and the packet headers are completely different. So what I did in this cycle is I split the rpmsg and the Virtio rpmsg implementation in the framework and the Virtio backend. And then I introduced the SMD implementation as one of the backends. And I have an upcoming G-Link implementation, which is what we need in the new Dragon board for communicating with some of the services. So we will have one API for talking to these point-to-point channels, and depending on how that stack was probed, we will use different wire format and different backends. There was some side effects of some cleanups and that. One of the other things that I think TI have 3 or 4 different out-of-tree implementations, or there are forks of them at least, is for user space to be able to access these point-to-point channels. It can be for debug interfaces or just for application logic that doesn't need any kernel handling of that. So we need a way to expose the rpmsg endpoints to user space. The TI solutions are to expose specific ones as character devices. There is protocol implementation, and there is one that's a mixture of sysfs and character devices. You have some that's specific, and then you can open additional or create additional character devices as you need. It's important that we must be able to handle a system with multiple remote procs, because that's quite common, and we must be able to handle. We can't only rely on the channel names to be specific, to have specific values. We must have something that's more generic than that. And mostly because we don't want a long list of hard-coded names in the kernel, that for this platform, these channels should be exposed to user space. And I don't even want to go to Rob with the suggestion of putting that in device tree. So we need some sort of mechanism for some sort of control interface for saying on this rpmsg instance, create a character device or some sort of handle that we can use for communicating on this channel. This is ongoing discussion, I would say, and hopefully we can. I think the more complex of the TI solutions or derivatives from the TI solution, I think we can massage this into something that will fit this model. Sorry?
You need a kind of export functions, like for example GPIOs.
Yes.
Omni-channel access.
Yeah, so something like that. Some way to have a control interface towards the rpmsg instance, and to tell that thing, or basically to be able to call create endpoint and destroy endpoint from user space, and then just expose that in something that we can read and write on. Most likely I would like that to be, if we expose those two functions to user space and we have, and then we just expose the channels directly as character devices. That would be
To have access to all mode with function X.
Sorry?
You want to have access to the whole mode with different access process.
Yes, I only want, this is only for when user space want to have direct contact with the other side. So whenever you want to do processing in the kernel, then you would need to write a driver there.
Common and straightforward. Pretty much the argument is the core API gives all what you need right now. So
Yeah, if you have some special thing where you need to do stuff in the kernel, or you want to expose that channel as something specific, some kernel, through some kernel framework, we already have a mechanism that's write to device driver for that.
From it, you are and it's okay to have. You must have, because most of the user-space application, for user-space application is standard. And if you have an external coprocessor or internal coprocessor, you will have the same application about to agent with your coprocessor with the same interface.
Okay.
So from it, we need such kind of
Okay. One thing that we've seen several times being useful is to be able to dump the incoming and outgoing data on these channels. We've used it quite extensively when doing Wi-Fi development on the Qualcomm platforms. So I would like to see a less hacky version of that, where we basically in our rpmsg send and in the callback would be able to dump the data. And if we can get that out as PCAP, so we can load it in Wireshark, that would be awesome. This I've not started writing much code on, so I only have the previous hacks. So if anyone wants to play along with that, feel free to do so. And that's it. Any more questions? Yes, it will turn out to be that, because I think you can have custom accessors for the V-rings, but then you have a buffer as well. Yeah, no, but yes, it will be shared memory only.
Yeah, that's the use case.
So,
Whereas Remoteproc doesn't really have to use the shared memory transport underneath. Is that implied or?
I mean, it's kind of identified. Does not really deal with communication per se,
you would have to implement your firmware operations as well on your own, but yeah, no, I would say that it's totally feasible for you to have a Remoteproc driver that turns on some power to something and feeds it a byte sequence over UART or wherever, and then when you're done, you pull the power. That would probably be a Remoteproc. I would say it depends on how, I mean, if you, on how what it exposes and how you want to control that thing. I mean, if it's a specific function that driver, or that firmware would expose, then there's, in most cases, there would be a specific driver for the hardware and the feature set. But
Yeah, it would be unnecessary abstraction maybe, but in theory there's nothing that says that you can't, we use that if you have like a really complex shared memory.
yeah, no.
But to come back on your initial point, as you decouple rpmsg and pairfile, I think that now we can use rpmsg interface to discuss with the external processor over SPI, UART, or anything else. And what is interesting with the rpmsg is that we have embedded servers, we can discover dynamically services running on the coprocessor. And I think that it makes sense in the future to propose some other interfaces other than shared memory, which is classic or mailboxes.
Yeah.
And to have rpmsg as a standard to discuss with any coprocessor.
So there is a, I mean, after these changes are done, then there is quite a lot of similarity between rpmsg and mailbox, in the form that you could very well use rpmsg as an API for your mailbox. I think the main difference between the rpmsg and the mailbox is this notion of it's coming and going. A mailbox, you just expect it to be there always. So we normally model those as some sort of platform driver. But if you have a more complex protocol, a more complex, say, packet format that is backed by a mailbox, then the rpmsg send and receive would probably fit that better than try to use the mailbox API. But I think the lifecycle part there is the main difference.
I mean, the difference I would say is also a little bit of logical transport, with the mailbox being your transports right now.
Yeah, but say that you were actually using mailbox for not only transmitting one value at a time, then suddenly you need that logic somewhere, so you have that. That's what I mean.
And we had long discussion with Jesse when developed the mailbox framework, maybe last year or so. And our mailbox was simply cross-centered basic shared memory, and at the end, mailbox drivers just support the cross-centered shared memory is when you have real-time code in the rpmsg, because the shared memory is not part of the IP. So if your IP don't have large file form, doesn't enter the mailbox framework.
Okay.
So for me, it's not completely similar.
Yeah, so
Something happened in the hardware spinlock.
yes, Lina have a patch that she wants me to merge. Other than that, no. So I think the only outstanding discussion we have is, so today the hardware spinlock frameworks expect that the spinlocks are used as you would normally use a software spinlock. That you lock it, and then when you're done, you unlock it. What Lina has is a case where she wants to lock it, and the other side should unlock. And that we don't support today. And the question that needs to be answered is that a property of that lock, or is it a property of the lock operation? Because the way the framework is modeled today is that you have a couple of lock operations, whether you want to grab to disable IRQs, and if you want to, or if you don't want to do that. And I mean, this would be, this could be bolted on as just another operation where you say lock without a spin lock, because the kernel implementation has a spin lock and then the physical lock, or the hardware lock. One could bolt on another function that skips that spin lock, and that would follow the design, the current design, but I don't think it would be nice. So I probably need to get back to that because it's now my problem.
Yeah, that's interesting. And why would somebody want to unlock on that? That almost feels like it's not
Because this particular use case,
still a waste. Like typically typical long
Yeah.
long or
Yeah, no,
one thread is very long.
but this specific use case is a synchronization between the kernel and the trust zone environment, where there is a lock in kernel and an unlock in trust zone to protect the order of that transition when we are going to idle, to make sure that when the kernel have decided that I'm going to idle, then we don't want a case that we have another core waking up and start executing in the kernel, and then the kernel telling trust zone that I was the last core down. So I can imagine that it took the Qualcomm engineers some time to figure out that race. So yeah. Thank you.